Okay, I think we can start. So I am connected with both Zoom and Teams. So good afternoon to students who are connected remotely. Those of you who are connected with Teams, please move to the Zoom room. It's better for you because even if I am lecturing also on Teams, it's not easy for you to follow. It's much better if you follow on Zoom. Okay, so good afternoon. I think we can start by making a brief recap of what I did last time. We had the first lecture, and the first lecture was focusing on why we are concerned by climate change. This is, in essence, the content of the previous lecture. Today I am using the micro, so I hope that it's also better for you. I prefer to use it because last time I had to raise my voice, and at the end of the 3 hours I was a bit tired. So we focused on the importance of climate change, why we are concerned, and we made a lot of also a lot of reviews, historical reviews of the literature. And today I am moving forward just by talking some more about the importance of knowing climate change. And we are getting into, today we are getting into the science, and much more into the science, not from a technical point of view, but a little bit into the concepts that allow us to know climate change, to know how it occurs, how it manifests itself, and what are the implications. This is the essence of today's lecture, and I will in particular talk about data, because in order to know climate change, we need information. And a big chunk of this information is data. This is, in essence, what we are discussing today. Next Monday, Professor Veronica Rossi will teach, and she will again talk about data with a focus on the climate of the past. This is another essential information that is useful for you to know climate change better. I will attend the lecture next Monday, but remotely, just to inform you that we are starting Monday with next Monday with the lectures given by some of my colleagues. I will teach again on March 14. In the calendar, there is in the schedule, it's mentioned the lecture by Professor Navarra. It will be postponed, but for now, just keep in mind, next Monday, Professor Veronica Rossi will be here to teach. Okay, so let's get into today's content. And this is my website. I just want to remind you very briefly how to get the information. And if we click on the tutorials of Science of Climate Change, we get into the list of the lectures. We are focusing on the climate change problem. I just want to introduce data and information by starting from the very final part of this lecture, which I didn't introduce last time. So let me just get back the PowerPoint presentation. I told you that this PowerPoint presentation is useful to teach, not really to study. So I just want to remind the concept because I think it is important. This is it is the presentation I used last time. I go quickly to the last lecture that I showed you. It was this one. Sorry, it was about the role of engineering. It was about the role of engineering, but anyway, we talked about tipping points and the role of engineering for predicting, let's say, for studying climate change. Today, as I said, I want to start with data, to talk about data. And why we are concerned about data? Because As I said, we need information. We need information to better understand how climate change is taking place. And this information, basically, it's like an experiment. When we get data, we get the result of an experiment. In this case, the experiment may consist in observing the reality, observing the truth. So we get observed data of some climate features. Think about temperature. We get observed temperature. It is the result of an experiment. Fortunately or unfortunately, it is a real world experiment, meaning that we may say that we humans, we are warming our Earth system, and therefore we are making an experiment. We are really making a real world experiment, and now we are observing what happens. So the experiment is to release emissions and then measure the increase of temperature. This is really an experiment. And I say fortunately or unfortunately is a real world experiment. Fortunately, because this is really, I mean, a real world experiment is telling us what happens in reality. On the other hand, I say unfortunately, because of course, if the experiment goes wrong, this is the real system where we live in. So if we, for some reason, if we cross a tipping point, we know what is a tipping point. It is a transition, we said, from an equilibrium state to another one. So if we cross it, it may be impossible to come back, we said. And therefore, to go back, we said. And therefore, this is, I mean, the unfortunate consequence of the fact that we are indeed dealing with a real world experiment. And I just want to emphasize that making experiments is essential to make progresses in science. Experiments are at the core of science. Usually in science, we make assumptions, and then we elaborate a conceptual basis. We have a problem to solve. Sorry, I have to start from this. We have something that we would like to know better, like functioning of a real system. And then we make assumptions, which means that we elaborate a conceptual basis, an idea. We elaborate an idea of how it works. And then we make an experiment to check whether the results confirm our idea. This is the essential step in science. Problem or target, because science sometimes operates for increasing knowledge, not only for solving problems. So we have a problem, a target. We elaborate an idea to explain the processes that we want to know better for the sake of solving the problem or the sake of improving understanding. And then we make an experiment. This is the essence. And when I say that we need data for studying climate change, it's precisely because these data are for us the experiment. Keep in mind that data, for now, I talked about observed data. You may think that I'm just referring to observation, only to that. No, data may be also data from mathematical models. An experiment may be that I run a mathematical model. I run a kind of equation, analytical relationship, and then I get the results, and I see if the results from the mathematical expression confirm my idea. And this is what we call in science a synthetic experiment. It's not a real world one. And you may say, oh, this is much better because I'm not risking to do anything for the real environment. On the other hand, you understand that if you make an experiment also in the lab, a small scale experiment, which it's not the real world, because even if you work in a lab or if you work with a PC, it's not the real world. What does this imply? Uncertainty. The real world is much better because I am really experimenting in practice what's going on. If I make a synthetic experiment, there is uncertainty. But still, these are data, these are experiments, and this is what I want to talk to you today. Let me start from the real world experiment, or how it's called in this slide, the natural experiment. And let me then focus on observed data. And this is, of course, the most obvious solution, because you may think that by looking back in our history, I can get data of what happened in the past, and this may give to me instructions, information on how the future will be. This is trivial. This is what we do for several branches of science. We look back. For instance, we may talk about internet traffic. We have now a lot of data on internet traffic, and we may try to predict the future, how it will evolve, by looking at what happened in the past. And this is, I mean, something trivial and natural to do. The problem is that the observation period of our observed data in climate is limited. And this is something really curious, because I mean, humans started in the far past to observe the stars, probably because they needed the observation of stars to get oriented, to solve some problems. But humans didn't think in the past of measuring climate variables. Think about measuring rainfall. It's much easier than measuring the position of stars. Observing rainfall is very easy. You take a tank, you put the tank in your courtyard, in your garden, and then every day you go there and see if there is water into the tank. And if there is water, you measure it with a simple method, with a simple rule. You measure.
Excuse me, Prof.
Yeah.
We are not able to see the presentation from home if you are.
This is strange. Let me just.
Actually, we were seeing the
PowerPoint,
the website.
Okay. Yeah. Okay. I'm sorry for that, because I shared the website and not the screen. Just 1 second.
Okay. Okay. No problem.
You didn't lose anything. I think you should see it now, correct?
Yeah, now it's okay.
Okay, you didn't lose anything. This is the first slide, actually. So, as I said, the observation period is limited. And this is strange because, I mean, our knowledge of climate would be much more detailed if we knew rainfall from the far past, or temperature. I mean, it is relatively easy to measure temperature, and I think it would be just enough to have qualitative observations of weather in the past, like if we had an ancient civilization taking notes of what was going on. I'm not talking about measures, just information would be fine. The problem is that we don't have this. And as I said, rainfall is relatively easy to measure. Okay, every day you have to go there and take a measure of the rainfall depth that fell in the past day. Okay, but it's easy. I mean, it's demanding because every day you have to do that, but it's easy. But if we look at the longest rainfall record in the world, it is the rainfall series collected in Padua in Italy. They started in 1725. So we have less than 300 years of data. It's nothing comparing to the history of humans, not to speak the history of Earth, is nothing. 300 years is nothing. I mean, so we can't really say what kind of rainfall we got in the Middle Age or we got 1,000 years ago. We can't say that, because we don't have any information. By the way, in Italy, we have the longest series of rainfall. In Padua, they started in 1725. I'm talking about daily observations. Every day, a person went there to take a measure in these tanks located outside. And typically, they were monks because, you know, this is really an everyday practice, and they needed dedicated persons to do that. And the longest is in Padua, as I said, and then we have Genoa, Florence, and Bologna, who started in 1813. It was clearly an idea that was developing at that time. So once that Padua started, they spread the voice, and then in Italy they started to measure in these other locations. In other parts of the world, they started later. So we have a good, I mean, we have a really strong information, a powerful information in Italy. Unfortunately, it's only related to Italy and only to these locations. And therefore, we say that our observation period is limited. Okay, and let me just say that the climate change debate would be completely different today if we had the idea of measuring rainfall 300 years earlier than 1725. It would be completely different, because one thing that we know, and the Professor Rossi, I think, will discuss with you, is, for instance, that in the Middle Age, there was a climatic optimum with a different climatic regime. And there was a shift in the weather from about 1300 to 1700. We went through a climate optimum, which means higher temperature. It is the medieval warm period. It is called medieval warm period. You have a link in Wikipedia. You have a page in Wikipedia to look at that. It would be really interesting to know how rainfall behaved at that time. Instead, we know that there was an optimum. Why? We don't have data, but we have information. We have information, and we have other type. Information means stories, narratives, and reports taken into the monasteries by, again, monks and who took note of the weather. But very brief notes, but they allow us to know that there was at that time an optimum. But we don't have records, observed records. Another thing that we know for narratives is that during the Roman period, there was a climate optimum. And it seems that the collapse of the Roman Empire was caused by several reasons, but one of them was probably climate change that provoked the worsening of the weather, with several floods occurring and the disruption of several agricultural practices. But again, we don't have data. And for instance, for the medieval warm period, we know that, but it is for Europe. We don't know if in the Americas they had the same situation. So we don't know if it was a global optimum or a local optimum. Data. Sorry, I moved. Okay. I talked about the series in Bologna. You can see the rainfall series in Bologna. I downloaded this data from the web. You can find the rainfall series in Bologna from the web. And if you draw a plot of the annual rainfall, which means the total amount of rainfall that fell during an entire year. So you get one number per each year. What number do we expect? It's about, on average, 800 millimeters. This is the total amount of rainfall that we expect on average in Bologna, 800 millimeters. And indeed, if you look here, a little bit less on average. You see on the graph, it's about 700, not 800. If you look on the graph, the progress, there is a lot of variability, up and downs. And this is another behavior of some climatic variables, which makes their analysis a bit complicated. Variability, what does this mean? It means uncertainty. We cannot make a prediction, a precise prediction. Like if one asked me, how much rainfall are you expecting in Bologna in 2022? I would say something around, on average, 700. But if I am asked to provide a precise guess, I would say I can't give a number. I can only say what is the average, but it may range from, look at the graph, from 200 millimeters to 1100. This is the range of variability. And you understand that if a process is flat, constant, think of a variable that is less varying, like temperature. Temperature is not so fluctuating. If you take the average temperature every year in Bologna, it's almost flat. It's easy to understand changes. It's easy to see changes. If something is almost flat, then you see any tiny change gets your attention. But with a graph like this, it's difficult to say, do you see changes? Maybe, but I would say, I don't know really. And look at the gray areas. These are long-term droughts. So if you look at this data, let's suppose that they are reliable, because somebody may say, this data may be not reliable because it's so long. And who knows? I mean, urbanization, if caused some changes. But if you assume that these data are reliable, one may say that in the past they had longer droughts than in the past 70 years. Why? We don't know. I mean, it's fascinating to look at the data. If you are passionate, you can find on the web a lot of data. And some of them are easy to download, some others are a little bit more complicated because some of them are stored in huge databases, and to navigate in these databases is not easy. But if you are passionate, there are a lot of these. And the reason why several people are so passionate about climate is precisely the availability of a lot of information. But now let me talk about another source of information which is interesting, because I talked about observed data and I told you, but I knew that I had to add something, that for the temperature in the Middle Age, in the medieval period, we can only rely on memories, on narratives. Actually, it's not true. There is a way to find an information that is alternative to data and to written reports. And this is the information that is embedded into the Earth system in the form of some kind of memory. And an example which is well known is three rings. And by looking at the width of each ring, you can understand the growth, the rate of growth, the progress of the growth of the tree. You know, some trees are very old, and therefore you can see that during a certain period they didn't grow up so much, and in other period they grew a lot. And this indicates a period where the climate was more favorable to growing living species or less favorable. And these are called the proxy data. They are not observed data, they are proxy data. I mentioned three rings, but there are also the ice cores. The ice cores are another relevant source of information. If you drill in the ice of Greenland and you take a sample of ice, typically they drill with a kind of pipe, and then when they extract the pipe, they take the ice from the deep underground, under surface, and then they analyze these ice cores, and by looking at some behavior of the ice and also composition in terms of isotopes, they understand the past climate. Another interesting field is limnology. If you take samples from the bottom of old lakes, basically what you get is a sample from the material that settled down during the history, the siltated material, so the material that went collapsed on the bottom of the lake, which is composed by degraded vegetable materials, etc. And by analyzing these samples, you get again information on the climate of the past. Proxy data are very interesting, but you should have well clear in your mind what is the difference between an observed number, an observed information, an observation, and a proxy information. The difference is that observation is an estimate of the variable you are interested in, taken by directly measuring it. So you make a direct measurement. You measure rainfall depth, you directly measure it. A proxy data is, as the term suggests, a proxy, meaning that you are not measuring the variable. You are measuring another variable that is supposed to be correlated with the variable of interest. And then you apply a relationship for an indirect estimation. So I estimate rainfall depth by looking at the width of the tree ring. But what I observe is the width of the tree ring. And then I have a relationship relating the width with the rainfall depth. And you understand that there is more uncertainty. It's clear. And keep in mind that when you look at the science of something, whatever it is, when you talk about science, science is always associated to uncertainty. Science is not associated to certainty. Science is associated to unknowns. I mean, if we knew climate perfectly, how it works in the climate system, we wouldn't talk about science of climate change. There wouldn't be the need to study it. Why we need to make science? To resolve unknowns. And then there is uncertainty. There is no science without uncertainty. And I also would say that there is no good science without uncertainty. When you are granted a scientific result, for sure, you have always to be in doubt. We say in science that uncertainty and confrontation of different interpretations in the face of uncertainty, it's what allows science to move forward. So a scientific debate shouldn't be seen as something negative. I mean, there is no progress in science if there is no debate. But anyway, let me go back to my main argument here, which is the fact that you have to be fully aware of the difference between an observation and a proxy data. Okay. Here you see a lot of links. If you're interested to expand, there is a lot of information available. And now, let me talk about a third way of obtaining information. So far, I talked about real world, either through direct observation or through proxies. Now I want to talk about models. Because a second way of making experiments, as I said, is through the math, through mathematics, through models. I mean, when we talk about a model, what is a model? Is simulation of the reality. It's something that is not the reality. It's something that we think may behave similarly. And there are different kinds of models. It's not only mathematics. For instance, several scientists of the past, they used to make experiments with small scale models in the lab. So for instance, I am an hydrologist, I am interested in rivers, in movement of water. It is usual practice in my field to reproduce the river in small scale into the lab and running experiments. This is very useful because it's an experiment that is expected to be similar, as I said, the model is expected to give a good simulation of the reality. On the other hand, by reducing the scale, you first of all make possible to make experiments that you wouldn't be able to perform in reality. For instance, sometimes we make experiments on what happens if I put a bridge over a river. And in the past, the bridge were interfering with the river flow. Now we try to make a single arch crossing the river without putting any pier, any foundation for the bridge into the river, but in the past they used to interfere. And then, of course, if you make a real-world experiment, you make the bridge, but then if at the first flood the bridge is flushed away, then it's not a good experiment. Of course, it's an experiment that requires a lot of money and a lot of risk. So the idea is I go into the lab and I try to set up the bridge in a small scale model, and I see what happens if I run a flood along the river. So this was the classical way of making experiment into the past. You may think, for instance, of Galileo, who went on the Tower of Pisa on the top to try to prove his theories by letting bodies falling down and seeing if there were differences in the travel time of bodies with different weight. And so he understood that the velocity of the bodies didn't depend on the mass, but only depended on the acceleration of gravity. And which is the same for a body of different weights. So these are, in a way, models of what is occurring into the reality. And up to recent times, mathematical models were not really much used, because what is the difference between these small scale models and a mathematical model? A mathematical model uses mathematical expressions to reproduce the variables. So it's not through observation of what happens in a simplified environment, smaller scale, etc., but it's computation, calculus. And this is possible for several disciplines and for many scientific disciplines. You set up a theory, your idea on how the experiment works. Basically, it is materialized within an analytical expression, and then you run it, and you get the result. And you may say, this is not really fascinating because it's much better to see. And you may say, this is more uncertain. Actually, there are situations where the mathematical model is providing a better approximation with respect to small-scale models. For instance, in my field, I talked about the bridge. There are mathematical models that are very good. Of course, you need to set up a theory, something that may look boring, but actually, if you get into it, and it is exciting. And this is what we did with the climate, because with the climate, unfortunately, we cannot perform small-scale experiments. And the real-world experiment, I mean, it's not easy. And in some cases, it's not possible. We cannot just say, let's reduce the emissions, let's bring them to zero and see what happens. And see how the climate evolves in 5 years. We cannot do that. Or we cannot say, let's close the Gibraltar, I don't know how to say in English, but yeah, okay, good. How did you say? Inlet. Okay, inlet, yes. Let's close it and let's see how the temperature, let's close the Gibraltar inlet and let's see how the temperature of the Mediterranean change. We cannot do that. And we cannot say, we cannot go into the lab and see, let's see what happens. Let's see what happens if I bring the CO2 concentration to zero. This is not really possible. I mean, it would be possible, but it's not representative of what may happen into the reality. And therefore, the idea is I try to set up a mathematical model. And this is the climate model. The concept of climate model is what you really have to try to better know, because I anticipate that the predictions that we make about the future climate, they are derived through climate models. all the predictions. When we listen from the TV or the media, by 2100, the temperature may be 2 degrees, the global temperature 2 degrees more than now. Or you may listen, for instance, from the Paris Agreement, that the target is by 2100 to limit the global warming to plus 1.5. And how do we estimate it? Through climate models. It is the only way to make prediction. And therefore, in different forms, I mean, they are different. There are several climate models, but the only way to make prediction is through these mathematical abstractions, mathematical expressions of the reality. And then you have to understand, if you really want to get experience, if you want to become a climate expert, you have to understand how a model works, how many different models they are, what is the difference, what are the limitations and the advantages, pros and cons of each model. This is extremely important, because otherwise, if you don't get this, you just have to rely on what the models say, but then you are not expert about the science. If you want to become an expert of this course is called Science of Climate Change, you have to really pay attention to models. And for instance, here you see a picture on the screen, and which is the predictions of future climate, future temperature, distribution of future temperature for the period 2081-2100, and this is increases with relative to the period 1986-2005 under low and high emission scenarios. I think that all of you know what emission scenarios are. We will talk about them later on, but basically they are predictions. The emission scenarios are prediction of the future CO2 emissions by humans. And therefore, we make different predictions. And you see that you have two figures. The upper one shows a lower warming with respect to the lower one, because the lower one assumes that you have emissions that are more significant. These predictions, again, are obtained through model. And look, one important thing, climate models are not really conceived for reproducing observed variables. So climate models are not meant to reproduce what happened in the past. They are conceived to make predictions for the future. And this is something that makes climate model a little bit different from I would say any other classical mathematical model, because a mathematical model is meant to reproduce a system, a process, the Earth system, so it should work for the past as it works for the future. I mean, if it gives a good reproduction of the system, it should also work in a very good way for the past. Actually, climate models don't work really well for the past, and for the reasons that I will explain to you later. But actually, I just want to give you one word: uncertainty. Climate models have a lot of uncertainty. And therefore, when you try to reproduce the past, you don't get a good match with the data. But for the future, they are expected to provide a good estimation of changes. This is another piece of information that you really need to know. I mean, you don't have to assume that a climate model is an instrument that allows us to make perfect predictions. This is not absolutely the case. And we don't have to expect perfect predictions. What do I mean for perfect? I mean that we cannot expect that a climate model will tell us what will be the average annual temperature in Bologna in 2050. It's not possible. If you talk about global temperature, it's already something more feasible. You don't have to expect that a climate model predicts the rainfall in Bologna in 2050. It's not possible. Why? Uncertainty. I mean, we are talking of climate. It is something that we don't know. We don't have data, observed data. So it is something that really, we don't have past observations. It's something that we don't know. You may think, but we should know everything. No, absolutely. I mean, when we talk about the Earth system, there are several unknowns in the Earth system. And for the climate, it's even more compelling, the presence of unknowns, because climate is chaotic. Stop. I said chaotic. What is chaotic? What does this mean? Okay, you may understand what is chaos, but actually there is a very rigorous definition for a chaotic system. And you may know, because it was widely discussed in the past, the famous example, I think, I don't remember who was, I would say the scientist who said this, who said that if a butterfly flies in Japan, an hurricane may be originated in New York. And this is precisely the feeling of what is chaos. Chaos means that you have a system where even a small perturbation here may originate a large change there. So if you have a small perturbation in Japan, you may have a large change in the system in New York. This is chaos. When small perturbations are magnified, they amplify, and amplify. This is chaos. It means that the system is, in a way, not unstable, but it's sensitive and affected by huge variability. Climate is chaotic, which means that even if in the model you make a minor mistake in representing a variable, then you can get a prediction that is completely wrong. And the climate system is chaotic, so there are some ways in which perturbations propagate that we don't know. I want to give you another example. As I said, I am an hydrologist, I'm studying floods. We still don't know what happens to water from rainfall to river flow. So we know that it's raining and somewhere we get flooded. But what happens in between, we don't know. Where the water travels, I'm not sure. Maybe that last Monday I already made this example to you. I'm not sure. If this is the case, I apologize. But where does the water travel? Over the ground or underground? We know that in some floods, we found some water that rained 2 weeks ago, not yesterday. And just to give you another interesting example, up to, I would say, 1500, Middle Age, people didn't realize that floods were caused by rainfall. They thought that floods were caused by emerging water from the deep underground. Why is that? Because, you know, maybe that people living in Ferrara, they were flooded by the Po River without any rain. And so they thought, but where does this water come from? They didn't know that in the Alps, there was a sudden outburst of water from the glaciers for some reasons. Okay, but now you have a perception of our sources of information: observed data, proxy data, climate models. And just beware that in all of these three cases, you have uncertainty. In the observed data, you have uncertainty because, you know, when we talk about daily rainfall, it may happen that you take a measure that is wrong, or the person that took the notes made a mistake in writing, or maybe the person who read the notes, hand notes, they made a mistake in reading, or maybe that the person forgot to go there and take the measurement, and then 1 day later they said, oh, let's make a guess. So data may be uncertain, proxy data are uncertain, climate models are uncertain. Okay, so these three types of information, all of them are uncertain. Okay, let's before talking about climate models, because I think this is something that, not I think, this is something that we will talk about extensively. Let me just make a final mention to climate impact, which is, let's say, another essential step for finding solutions to the climate change problem. So we may get data on climate change, and then we have to estimate the impact in order to find the solution. And this is something that the engineers are particularly concerned about, because you know, if you want to identify a solution, you have to identify a problem, and the problem is not from the human society a change in temperature in itself. The problem is the impact of the change in temperature, which may be an impact on our health, direct impact, maybe an impact on rainfall, and therefore there is an indirect impact, and maybe heavier rainfall, maybe less rainfall. And it is not easy to identify what is the impact of climate change. And keep in mind that here you have two graphs. On the upper one, you see the losses. So one way to quantify the impact is to quantify losses. And in this case, it's economic losses. And you see the losses from weather disaster worldwide from, I would say, 1980 to 2019. This is a graph prepared by myself. These data are publicly available. And they are corrected by inflations in order adjusted to compensate for inflation. And you see that in the upper graph, there is an increase of the losses, which means that indeed weather-related disaster increased in terms of losses, economic losses, which means that it may be climate change. But in the bottom graph, you see that the same losses are expressed as percentage of the global GDP, gross domestic product. And you see that it is flattened down. Why? Because the losses increased, but there might be two reasons for increase of losses due to weather disasters. One is increased frequency of the disaster, and another one is what we call increased exposure. It means that the same flood in 1980 causes less damage, less economic damage than the same flood in 2019, because it's the value of the flooded areas that is increased. So understanding the impact of climate change, it's another tough issue. I give this information to you because I want that you are aware that we are talking of really difficult questions where science plays an essential role. And the only way to address the climate change problem is precisely to strengthen the science behind it. I just want to give you this awareness, because sometimes, especially today, we think there is a global, I would say global movement that tries to disqualify science, distrust science. Actually, science needs to be trusted, but science, in my opinion, of course, science means also debate, confrontation of different opinions. So on the one hand, I would say that these debates that are ongoing on climate change are what we should expect. It's fine. It's fine. Of course, when the debate becomes confrontation based on opinion that are not based on science, then it becomes counterproductive. So debate is fine, but debate supported by science. Okay, let me go to the next one. So this is the PowerPoint that I used last time. Just 1 second, because I'm not sure. Yeah, I didn't close anything wrong. I just closed the browser. This is not precisely what I wanted to do, but we can restart it. Just 1 second. Okay. And let me click now on the next one, climate models. And this is another web page. I have a PowerPoint also for this. Just 1 second, I download the PowerPoint here, and then I open it here. Good. Okay. Now we are focusing on climate models. I already gave you some information. Now I'm trying to get into the details. And before I move forward, let me make an essential premise. A model has an essential advantage over observations. A model can be used to make predictions. And not only to reconstruct the past, but also to make predictions. And we need predictions. So let me say that climate models is something that we really need. In a way or another way, we really need models. And by the way, in science, this is a usual practice. Models, as I said, may be mathematical, may be different nature. In this case, I'm talking about mathematical models. And what is a mathematical model? Here you can see a definition that I got from Wikipedia, which I think it is nice reading, because in this way, I hope to be clearer. A mathematical model is a description of a system, fine, using mathematical concepts and language. The process of developing a mathematical model is termed mathematical modeling. Okay, now what is the history of mathematical models? There were mathematical models devised in the far past. You know that arithmetics and mathematics are ancient theories. But mathematical models have a problem, which is the calculus. The calculus in the past took time. Recently, we got a lot of computing power, but this is very recent. I mean, the first personal computers were introduced in the 60s, but they were something not comparable even with this PC that is now on this desktop. Modern computers were introduced about 30 years ago in the 90s of the past centuries. And this was the time when the PC got into our houses with no web at the beginning. And therefore, this is an instrument, it's a tool that is available from yesterday, basically. And we are used today to assume that some things that we now take for granted, like the TV, the personal PC, they have been part of our history for a long time. Actually, this is a recent development. And this computational power basically empowered mathematics and expanded the possibility to apply mathematical models. This is why these are relatively recent. This is why we didn't have any mathematical model for climate up to 30 years ago. And now we have these global instruments that are trying to simulate the climate of the whole Earth system. Okay, typically a mathematical model has an input and generates an output. Here you see that the model is indicated as a black box. Actually, there are several different types of models. And instead of this black box, you may see something empirical. I mean, input, output, I find an empirical relationship. In the past, this was the classical structure of models in order to simplify their related computation requirements. They made it simple, and simple means empirical. By the way, this is still the method, the empirical relationship with which we predict several natural processes, like sediment transport in rivers. It is predicted through empirical relationship. Empirical, what does this mean? It means that it has nothing to do with the reality. It's just an expression relating to numbers. Perfect. But the model may be more sophisticated. And then if I want to make a model more sophisticated, what I am expected to do, trying to understand how a system works in detail and describe any single detail. Okay, and these are called process-based model, based on our understanding, or as you see in the slide, physically based. Given that we are talking of climate, the science of climate is mainly atmospheric physics. So this is why here I wrote physically based. You may say that the physically based or process-based model is more reliable. Actually, it depends, because given that they are more complicated, uncertainty is also related to the level of complexity. The more complex is a task, the more you are uncertain of achieving it. When the task is quite easy, quite simple, you have more confidence that you will complete it. The same for climate. If I try to describe the details, I expand uncertainty. Keep in mind that we are talking of something that it's changing in space and time. Climate, rainfall, temperature is changing in space and time. Changes in time are often called non-stationarity. This is an improper definition, but let me just say that. Changes in space are called heterogeneity, are identified with the term heterogeneity. But keep in mind this spatial and temporal variability, changes in space and time. You know from your experience that when the weather is variable, it's more difficult to predict. Sometimes you listen to the forecasting of the weather. By the way, it improved a lot during my lifetime. When I had your age, the forecasting of the weather was absolutely unreliable. And today is amazing, amazing. And basically, the meteorologists, they say that every 10 years, they gain 1 day of prediction. So meteorology in the 80s of the past century has less 4 days of prediction with the same reliability. Okay, so, but you know that when the weather is variable, sometimes people say there is a lot of variability, so the prediction is unreliable. The same for climate. There are climate variables that are very variable. I already said this, up and down, or up and down in space or in time. And when there is a lot of variability in variables, then it's more difficult to predict. Temperature is easier. So this is another thing that you have to consider. Climate models are quite good in reproducing temperature. They don't have the same precision in reproducing rainfall, wind. Just think about the variability. Okay, this is something that you should be able to understand yourself, no matter what is your background. Think about the complexity of a process and the variability. Something that, as I said before, it's flat, is easy to predict. Temperature is easier. Rainfall, it's not flat. In summer, sometimes you know that you may get completely wet under a storm and 1 kilometer far, they have the sun. This is variability. Okay, so these are climate models, and the history is quite old, and very simple models were already developed by ancient civilizations, because they had some, for instance, here you read, Greek astronomers and geographers understood that the shape of Earth is spherical and connected climate to the inclination of the terrestrial axis. This is already a model. Of course, these models were not really demanding in terms of calculus, of computational power. They didn't have it, so they had to save computational power. If we go back to the 19th centuries, scientists developed some mathematical models of energy balance and radiative transfer. They were very simple models. We will see an example in a while. Very simple models that allowed to make a balance of the energy for the Earth system. You know, energy of the Earth system comes from the sun and internal energy that is stored in the globe. And it is relatively easy if you consider the Earth as an isolated system to make a balance. You consider it as a unique system. You consider the energy that comes from the sun, which is the great majority. And you estimate the radiation from the Earth that goes back to the space. And it is relatively simple. You consider like a single body with some energy entering in the form of heat and energy going out in the form of the radiation. It is quite simple. And if we instead consider about computer simulation model, as I said, they were introduced in the 60s. Actually, here I'm saying in the 50s of the past century. But as I said before, from about 30 years ago, we had really a spike in computer power, in our capability to perform very complex computations. And it's since then that we really started developing sophisticated models of the climate system. Let me just check the next one. But I just want to anticipate one thing already at this point. When I mentioned the simple model of the globe as a unique body, this is a model that considers the Earth system as a unique entity. But in this way, you cannot describe internal changes. You can describe global temperature of the atmosphere, but you cannot describe the variability from the United States to Europe. Because if you consider the system as a unique entity, you get a number for temperature, not two numbers, not many numbers. If you want to get a detailed description, you have to split the system and consider the system as a puzzle, where each piece of the puzzle has a value for temperature. But this is quite complicated because, like in a puzzle, you cannot put these pieces randomly. If you have in Bologna a temperature of 20 degrees, you cannot say that 10 kilometers apart, it's minus 20. Like for a puzzle, you have to compose it by taking into account the state of the neighbors. The state, I mean, the status of the neighbors. So you have to allow for exchanges, because if I have very warm in Bologna, part of the energy, of the heat energy, gets spread around. So you have to connect these pieces, not only by their position, but also by their exchanges. And the same for water. If you want to describe water flowing, and you want to describe the velocity of a river in several places, you cannot consider the river as a unique body. You have to split it, like in a puzzle, and you have to connect the pieces to allow water flowing from one piece to the neighbor. It becomes complicated, fascinating, but complicated. And you can understand that if you make a small error in Bologna, then when you move 10 kilometers apart and then 10 more, 10 more, 10 more, this error may expand. This is classical in mathematical models. So you make a minor mistake here and the mistake is amplified there. Now, climate models, precisely for this reason then, are expected to describe several different processes. It's not just a unique entity describing only temperature. If you want to describe temperature in detail, you have to describe also evaporation, because evaporation takes heat. And you have to describe glaciations. You have to describe snowmelt, of course. And therefore, in the climate system, classically, we can identify 5 main subdomains, which are listed here, or I would say, sorry, it's 5, yes. Atmosphere, cryosphere, hydrosphere, biosphere, technosphere. So, what is the atmosphere? It's the layer of gases commonly known as air surrounding our planet and retained by gravity. And it's composed by 5 main layers. And you see in the picture, exosphere, thermosphere, mesosphere, stratosphere, troposphere. You don't need to remember all these terms for your exam. Absolutely. But I just wanted to tell you that, of course, we usually represent the atmosphere through 5 layers. What is the implication? It means that a mathematical model cannot describe the atmosphere as a unique body. It has to describe these 5 layers with exchanges of energy, heat, etc. Okay, this is the atmosphere. The cryosphere is the domain of water in solid form, including sea ice, lake ice, permafrost, frozen ground, etc. There is a wide overlap between cryosphere and hydrosphere. Hydrosphere includes the mass of water found in the Earth system, which can be above the Earth in the form of water vapor, for instance, or in the form of spray, water spray, and water above the surface of the planet and underground water. This is the hydrosphere. And we know that it covers in liquid state about 70% of the Earth's surface. So it's an important matter. And in the southern hemisphere, there is a dominance of water. Keep in mind that when I describe these systems, there are intersections. And it was just mentioned, intersection between cryosphere and hydrosphere. The biosphere, also known as ecosphere, encompasses all ecosystems, means living organisms. It is the zone of life. Of course, there is a large intersection, a large overlap with the other spheres. And the last one is interesting, the technosphere, sometimes also referred as anthroposphere. It's a new concept, relatively new. It is the part of the environment that is made or modified by humans for use in human activities. And of course, there is a strong overlap. It is important because we know that anthropogenic impacts are really shaping the Earth system now. In terms of extension, maybe it's less important than you think, because we live in cities, and it is unlikely that we go to visit very isolated places. It is unlikely. So our perception is that most of the world is urbanized and impacted by humans. But actually, there are large part of the world. So just 1 second, because I see something in the chat. Okay, it is old. There are large parts of the world that are completely unimpacted, and they are also very often close by, but we don't see them because we are not interested. This is a paradox, because most of the humanity is, okay, let's say most of us, I don't want to speak globally, most of us are concerned about the environment, but most of us are not interested in the environment. because when we go for tourism, it is very unlikely that we go and visit places that are where the anthropogenic impact is very, very low. I give you an example, just close by here. There is just above the Faculty of Engineering, the School of Engineering, there is wood that is protected because it's considered a replication of a pristine environment. Why is that? Because the faculty was built in 1930 and they bought a huge area in order to build the faculty. And I think they were obliged also to buy the wood here, which is very steep. They were obliged because when they wanted to acquire the land here, the flat land where to build the building, they probably had to also buy the wood. And when they bought it, they just forbidden the entrance to people. They just banned the entrance to people. And it looks like only a few persons in the past 100 years went there. And you can see the wood just above here. And it is really not advisable to go because it's a little bit risky. Because if a wood is completely abandoned, then it's a bit risky. There are trees that may fall down, and it's not also easy to get there. And in the Alps and also in the Apennines, there are valleys where probably just a couple of people every year go there, but they are not visited because they are not attractive, because they are unhealthy. They are. So, I mean, if you look on Google Earth and you look at the extension of the cities, even in a very urbanized place like Italy, and you compare with the total extension, it's not that much. And this is this paradox, I mean, that we like to live in cities, we like any form of commodity, but we are very concerned by the environment and we are not interested in it. And I can tell you, because I took the initiative to sometimes go in places where they say nobody goes there. And it is very interesting because you really perceive what the natural environment is about. It's absolutely risky. You have to be very careful. And when you get the perception that if something happens to you, you don't have the mobile phone getting the signal, and you have to be careful because if you broke one leg, then it's a problem also to rescue you. It's very interesting. But in any case, the technosphere is important. It is important because even if the anthropogenic, the part of the globe that is impacted by anthropogenic activities is small, the impact is still large. We know that because the emissions are spreading. They can really go into the woods of the Faculty of Engineering. They don't care about that. We talk about water. Just let me give you an information that is very useful because the climate is shaped by water. The water cycle plays a relevant role in shaping the climate. And also most of the impacts of climate change, they hit humans through water. Just let me give you just a very, only this picture, just a little bit of information on the total global water. Total global water is 97% salt water. Fresh water is just, you see the left column, 2.5%. If you expand this 2.5% in the middle column, you realize that a lot of this 2.5%, a lot of it, 2/3, is glaciers and ice caps. Groundwater is 30% of this 2%, so it's less than 1% of the total water available. Surface water is 1.2%. So surface water is really tiny. If we expand surface water in the third column on the right, you see that there is still some permafrost, some water that cannot be used. Most of it is in the lakes. Rivers, it's only 0.5%. Of 0.5 of 1.2, and the 1.2 is 1.2 of 2.5. So you see that water in rivers is really tiny. On the other hand, this is a picture of volumes. It's not only volume that is important when you talk about water, and also climate variables. And this is the information that I want to give to you. Because if it was only volume, you couldn't explain why rivers are so less important, while most of the water for civil use comes from rivers. So why? How can most of our water uses be covered by river water with a so tiny percentage? Because this picture doesn't give you an idea of flow. It's not only volume that is important when you describe a value. The most important thing is flow. I mean, if I have a reduced volume, but it is flowing very quickly, I can fill a tank in no time. And flow means renewable. So this is why when we use groundwater, we are very concerned, because groundwater flows at a very small speed. River water flows quickly. So a climate model is not expected to describe only volumes. It has to describe flows, which is more difficult. But still, I think this picture is also useful because it gives to you an idea of the distribution of water. Most of the water is in the oceans. By the way, when I teach water resources management, I say once that we will be able to desalinate water quickly and efficiently and in a cheap way, we will have resolved any water problem in the world, which means that we will have resolved most of the international conflicts. Okay, now, these 5 subdomains of the Earth system, as I said, they are open systems. Open means that the quantities that we describe can flow from one system to another. Let me make again the example of water. Water is in the hydrosphere, but can flow in the atmosphere and can flow in the biosphere. These exchanges must be represented by models. So these are open systems that are tightly related to each other with exchanges of physical quantities like mass, heat, and momentum of energy. Momentum, let's forget it. It's something already probably too much technical, but momentum is related to flow and energy. Energy is more understandable. Now, let me make it clear. The climate system is driven by solar energy. All of these processes, they work. They need energy to work. They need energy, and it's all of this energy that drives the climate system comes with the sun. Okay, you may say that it may happen that a volcanic eruption releases energy in the atmosphere, and this is energy that you can't really say that it comes from the sun, because it comes from the internal part of the Earth. One may say that it came from the sun some time ago, but actually the main engine, the main provider for the climate system is indeed the sun. And this is important. Why? Because we can really try to understand how the climate system works, but it's important to know what is the fuel, what is the propeller, because it's clear that changes in climate caused by the humans, I mean, they have to be confronted with the changes that may be caused by the sun. And we know that the energy that comes from the sun is subjected to changes that we know only a little. And therefore, it is important to know this, because it's important to know what is the fuel. Some of the zonal energy is reflected back into the space, as I said before, while the rest is absorbed by the climate system and re-emitted as heat. Part of the reflected and the emitted energy is trapped by the Earth greenhouse effect, which causes, as we know, global warming. And this heat dynamics is what determines the temperature of the Earth. So if we think about temperature, it is an exchange of energy that comes from the sun, part of it is radiated back, and part is trapped, part of what is radiated back is trapped by the atmosphere and kept there. Why I'm giving this information? Because you need to understand how a climate model works. Understand? Let's say you need to get an idea, okay? Now, Earth is eaten by the sun not in an homogeneous way. It is eaten somewhere more than somewhere else. So there is an odd distribution of the heat that comes from the sun over the Earth. And therefore, some parts of the Earth receive more energy, and therefore there are temperature differences. But the system tends to reduce these differences by transporting heat from the parts where there is more heat to the part from the warmer part to the cooler parts. And then this heat transportation originates currents in the atmosphere, in the ocean, and etc., and originates what are called global weather patterns. There is a global flow of air, of water into the oceans, and this global movement of flow brings energy from one place to another place, and it's something that we need to describe in the climate model. And I want to give you an example, which is not listed here. Some time ago, I talked with an oceanographer. We just missed the plane. We had to wait a lot of hours in the airport, and we knew each other. And then he said, "Oh, given that you are an expert of water, can you please tell me an estimate, a local estimate of the amount of groundwater released into the ocean?" And I said, this is a very difficult question because we can give estimates of surface water released into the oceans because we can measure the flowing rivers, but we cannot measure the groundwater flow direct from the land to the ocean. And he said, this is really a pity because I am now working on a global ocean model and I am neglecting these exchanges. And he said, you know, neglecting these exchanges, I feel like there is a considerable approximation. And it is still like that. This conversation was like 20 years ago, 15 years ago, but still we are in the same situation. Still, we don't have a model that is capable of estimating the release of ground fresh water from the land to the ocean. So we rely on guesses. And in a climate model, this makes a huge difference because it's chaotic. Therefore, if you misrepresent some exchanges of heat into the ocean, it may end up with considerable approximations. It's chaotic, and this is what is written here. And this picture is an example of a turbulent flow. It's an airplane, and it's an airplane releasing a tracer, and this tracer shows what is the turbulence of air caused by the presence of the airplane. And you know, turbulence is an example of a chaotic system, something that we cannot really describe in detail. We can describe it statistically. And this is a behavior of chaos. You can describe pattern, tendencies, statistics, but not really details. And of course, this originates uncertainty. I want to make a long story short. Just want to emphasize what are the sources of uncertainty. Can you think of a mathematical model describing this red plume? Very difficult to describe it in detail. You have to approximate average concentration, maybe, of the tracer in a sphere around the plane, but not really a local description. And therefore, climate models usually don't have a spatial resolution that is very fine. How do they work? The climate models. I would say, let me check. Okay, this figure, I wanted this figure. They work not by considering the globe as a unique entity. Given that they aim to give a description of variability, temporal and spatial variability, they discretize, we say, they split the globe into a puzzle, as I said before. But this puzzle is extended not only to the surface, we have a puzzle for the surface, and then we have a puzzle for the atmosphere. You see the gray part that is above, around the globe. This is the atmosphere. And the pieces of the puzzle may have the same position and the same dimension, but we need mathematical representation for different layers. And we don't see the underground layers. If you want to describe the underground water flow, you have to go in the underground with another layer. And the atmosphere is described by 6 layers. So you have several layers of this puzzle, like several puzzles, one above the other, and they are connected in any direction. In the direction on the left, forward and backward, and along the vertical direction. So in the 3 directions of space, you have connections, links. And therefore, we say that these are 3D models, 3-dimensional models, because they describe the variability in the 3 dimensions of space. Sometimes, in order to emphasize also the dependency on time, we say that the models are 4D, 4 dimensions, 3 dimensions of space and 1 dimension of time, meaning that the models describe space and time variability. And any piece of this grid must take into account what happens in the neighboring pieces of the grid. Above, below, longitudinal direction, transversal direction. 3D models have a lot of connections. In each of the grid, you solve mathematical equations. You apply mathematical equations, but the input data come from external drivers and also from the neighboring cells. They are much complicated. And this is why at the beginning, they took to run like 1 month of computers running in parallel, several computers running in parallel for 1 month before providing a simulation of maybe 1 year of climate. And this is complicated. But it is also difficult to limit the spatial extension. You need a global approach. You need a global representation. And this is how they work. Let me make a break. And then, do you have any questions so far? Good, let me make a break then. And also remotely, if you don't have any question, let's make a break of 15 minutes and we see each other at 4:30. Yeah.
Excuse me, Professor?
Okay, here I am. So, I just want to mention that these models, these global climate models, are often identified with an acronym, which is GCM, that stands precisely for Global Climate Models. And the equations of GCMs are those which describe the evolution in space and time and the exchanges between one piece of the puzzle to the next ones of relevant atmospheric quantities. And I just wanted to emphasize once again that the reason why we use these grids to describe these processes is precisely to describe variability. Because otherwise, if you consider the process as a unique entity, you cannot describe the internal variability. Okay, now what is the size of these boxes, of these elementary pieces of each grid? And the size of the boxes of the grid, of each grid cell, decreased with the increasing availability of computing power. And therefore, of course, the smaller the grid cells and the higher their number, and therefore the higher the complexity, the number of equations, the number of fluxes exchanges to describe. And the modern models have a size projected over the land of about 100 square kilometers, which mean a grid cell of 10 kilometers, more or less. There are some cases where some models that have a finer resolution, some models have a variable resolution. So they adopt a larger resolution over the ocean and a smaller resolution, a finer resolution where they need to define processes with more detail. The previous generation of models had larger sizes. So if you think about a dimension of the grid cell of 100 square kilometers, you also get a perception of the level of variability that they can describe. I'm talking about the last generation of models, 100 square kilometers. It means that if you want to describe changes that occur within 100 meters, these models cannot. They can describe changes that have a spatial span of about 10 kilometers. I cannot describe a change that is taking place in 500 meters. And this is indeed relevant because, for instance, if you think about rivers have not an extension of 10 kilometers in the lateral direction. And if you need to describe these changes or changes in vegetation cover that may occur at finer spatial scale, you need more detailed representations. And this is done when needed by increasing the resolution at the local level. Usually this is done with another model. So we build another model that takes the input from the GCM and elaborates a finer description. And these are called limited area models. Now, what kind of equation do we use? What kind of mathematical representation do we use to build these models? We can call them the constitutive equations. And of course, you may remember from your studies in mathematics that if you want to describe one variable, you need one equation. If you want to describe two variables, you need two equations, and so forth. So the higher the level of details and the higher the number of equations. Now, what kind of equation can we use? Empirical relationship, as I said, like a relationship between input and output, but also physically based equations and the process-based equation, the equations that tend to emulate what really happens. And the candidate laws are conservation laws, conservation of energy, conservation of mass, conservation of heat. These are the candidate laws. And what is a conservation law? A conservation law states that a particular measurable property of an isolated physical system does not change as the system evolves over time and space. Isolated means that you don't have exchanges with other systems, or if you have exchanges, you have to account for them. You can express a conservation law for a non-isolated system. You have just to account for the exchanges with other systems. If the system is not isolated, it is in contact with other systems. But if you don't have a strong scientific background, let's just realize the concept of conservation of something. It is easy to think about conservation of water mass. Conservation of water mass, we know that water in the Earth system is conserved. And therefore, if it flows from one system to another, we can use a conservation law to describe this flow. So basically, what they do in a nutshell, what climate models do in a nutshell, is to describe how quantities propagate through the climate system, like water, how water propagates through the climate system, through conservation laws. So I imagine that water is conserved. So if I lose water from the ocean, then I may transfer it to the atmosphere through evaporation or to the land through pumping. This is what they model do. They describe how energy and other quantities like mass propagate through the climate system. Of course, we have to identify what are the relevant processes that we want to describe. It is a complicated system, but we can simplify it. By simplifying it, we obtain approximate descriptions, partial descriptions, which in a way, being less complicated, exhibit less uncertainty. Still, you need a lot of computing power to run these models. It's not something that can run on a personal computer. I'm talking about the last generation of models. If you take a very simple one, may run over a personal computer, but the last generation of models requires really a lot of computational requirements. And therefore, typically these models are run by a few research centers. You may have heard that recently the European Climate Services provided by the European Center for Medium Range Forecasting, they decided to allocate in Bologna the core of their computational resources. It is impressive. If you visit it, it's several huge rooms which are completely full of operating units of computers. Just with their operating units, they require a lot of energy. There is a lot of noise given by cooling, and really a lot of energy to cool them and run them. It is highly impactful because they take a lot of energy and therefore there is an impact, but it is an excellence center for computation that can run these models, but there are not many of them. So you don't have to think of millions of models running to predict the future climate, but you may think of tens of models, not more than that. Okay. What are the input data, input and output data? I talked about the model, which is what I indicated before as a black box, and then I talked about an input and an output. Input data are the driving forces for the climate, solar energy and solar forcing, which is quantified by estimating the solar activity and also the future solar activity. We also need to estimate how much energy is trapped by the Earth system in the atmosphere through maybe the greenhouse effect and in the body of the Earth. And there are other driving forces for climate, which basically regulate through external to the climate, external forces, regulate how the climate system evolve. And I think that a relevant example of such driving force is the concentration of greenhouse gases in the atmosphere. It is relevant because it is the reason why we are concerned. It is the reason why we think that the anthropogenic effect on climate takes place. And the most known greenhouse gas is the CO2, the carbon dioxide, but there is also methane, and there are other gases and also aerosols that are emitted when burning fossil fuels or making several other activities. CO2 is an essential ingredient of our atmosphere. It has always been there because CO2 is produced also by living species. It's produced by several natural processes and also by anthropogenic forcing. And of course, the concern is that today the emissions by anthropogenic forcing may have increased a lot, therefore contributing to the current concentration of CO2 in the atmosphere that is raising a lot. Okay, now, if emissions are important and they are a driving force, they need to be predicted, like the solar energy is to be predicted. But solar energy is in a way easier because we can assume that it's more or less stationary, with some seasonal variability depending on the part of the interested part of the Earth. But for anthropogenic emissions of CO2, we need to make predictions, and this is not easy. We can rely on the past pattern and project it into the future, but actually, there are several predictions that can be considered, and they depend also on mitigation policies. So what we do is to make predictions about the future CO2 emission, basing on our predictions of societal development and mitigation policies. And then there is a lot of output variables that are produced by climate models. And you may get easily a list from web sources. If you are interested, you may look to the Coupled Model Intercomparison Project, CMIP, and in the website they provide a lot of information about what is predicted by climate models. Keep in mind that the prediction of a climate model is conditioned by our current understanding and is conditioned by the assumptions that we make on the functioning of the climate system. And you may ask me, is there a way to check if they are correct? Actually, in view of what I already mentioned to you, that they are not at this stage conceived to reproduce the current climate, actually there is no comprehensive way of checking them. To be more detailed, for some of the variables, you may find the way of making a check, and notably for temperature, you can find a way. You can meaningfully test the simulation of past temperature. You can test if the models are able to reproduce the global warming that we have observed. You know about global warming. I didn't make an introduction to it, but you know that especially in the past 30 years, there has been a significant increase of the average global temperature, and some of my colleagues will talk about it. And for temperature, there is a way to check. Why? Because temperature is less variable, as I already mentioned, and therefore, and also keep in mind that the climate models were conceived precisely for reproducing the temperature, and then they became more and more detailed, and now they reproduce a lot of other variables. Temperature is easier and can be checked. And I can safely say that we can put confidence on prediction of temperatures because, as I said, there has been some testing. And also we have a lot of data to make the check. For other variables and for rainfall, for instance, the variability is so pronounced and we don't have much data to make a local check. So temperature is fine at the global level. I'm talking at the global level, average temperature. If you go to the temperature in Bologna, there is, at the local level, there is more uncertainty. But the checks that we tried to make so far on the what we call the hydrological variables, rainfall, river flow, water resources, here we cannot say that we were successful in checking. And therefore, there is not a real way of understanding if these models are good in producing the future of rainfall, which means also the impact of climate change, because, I mean, as I said, most of the impacts are through water. Most of the impacts of climate change on human society take place through water. Okay, and what is the time step? I talked about the spatial resolution, and what about time? The typical time step is 30 minutes. And so it means that you can describe variables with the time resolution of 30 minutes. Actually, it's quite good. But of course, you know, at final time scale, there is more uncertainty. So if you describe variables over a long time span, like annual rainfall, you get less uncertainty with respect to rainfall at hourly time step. And so for this reason, the output of climate model usually is not presented, as I said already, is not presented in terms of point and time predictions. It's presented in terms of statistics on change. And this is the real usefulness of climate models. You predict not really the future value of the variable, you predict the change. And I think that from a scientific point of view, this is perfectly fine. A scientist can say, under certain assumptions, and given our current knowledge on the processes, I predict that if emissions do not decrease in the future, there will be changes in temperature, rainfall, etc. This is perfectly fine. So we are not predicting the reality of the future. We are predicting changes. And I mean, this is perfectly fine, but this is not what is usually communicated. Usually from the news, you get the communication that in 2050, there will be more rain. Or sorry, this is fine. In 2050, we will have an higher frequency of floods. You cannot really say that there will be a flood in 2050. You can say that the rainfall will increase, but then the rainfall causing floods will increase, but then turning into floods implies going at a more detailed description, at the local level description, which is not really what this model can give. Okay, let me give you an example of a climate model, because I think it is interesting to make a break and give an example. And this is a model that considers the whole Earth system as a homogeneous entity and is based on the concept of radiative equilibrium. So if you look at this very simple equation, okay, it may look complicated to you, but actually it's very simple. And let me just explain what are the symbols. S is the solar constant, which is the incoming solar radiation per unit area. It is a well-known value at the global level. Okay. A is the Earth average albedo. The albedo is the fraction of solar radiation that is reflected back. It varies from 0 to 1, and it is about 0.3 for the Earth. R is the radius of the Earth, which is about the number that you see there. You don't need to remember this relationship for the exam. Absolutely, it's just an example. Sigma is the Stefan Boltzmann constant. We know the value, it is what you can see there. And epsilon is the effective emissivity of the Earth, we know the value. And then we can solve for temperature. And if we solve for temperature, it is easy. You just have to substitute in the relationship. Pi is the constant 3.14. You just have to substitute in the relationship these numbers that are given there, and then you get an explicit representation for temperature. And this is the explicit representation. And if you solve it with the numbers that I gave in the previous slide, you get an average Earth temperature of 15 degrees centigrade, which is fine. I mean, it is more or less the average temperature over the Earth. And so this may allow you to estimate changes in the Earth temperature that may occur if you change the albedo or if you change the solar radiation. It is a very instructive model. And of course, it's global. So it is simple because it's global. It doesn't describe what happens at the local level. It doesn't describe what happens as time passes. Any of these variables, A, S, sigma, are considered to be constant, and then you get a unique value. But you may use this very simple model for studying, if you change the solar radiation, what happens to the average temperature over the Earth. And keep in mind that global warming, we are talking about an increase of the global temperature from 1850, after the Industrial Revolution, that is about 1 degree. 1.1. We are at 1.1, I think now. I don't remember the precise number for 2021, but we are around that. And so you may understand what is the order of magnitude in terms of changes in solar radiation that is needed, or in terms of changes of albedo that is needed to compensate. And of course, the GCMs are not like the model that you see here. They are adopt a distributed description, and therefore they discretize the globe. They are much more complicated, but actually they are complicated because they put together a lot of simple equations. The individual equations are not much more complicated than the one that you see on the screen. But the problem is that they put together many of them, and they also have to account for exchanges. So any computation, once that they run a computation over a grid, they have to transfer the result to the neighboring grid and run the whole model. And this is why they require a lot of computational resources, not because they are, I mean, the equations are complicated. It's a number, it's a discretization. When you listen somebody mentioning mathematical models, you know, you usually have the feeling that they are something that is really complicated, is something that we cannot understand. Actually, it's not like that. They require enormous computational resources, but the concepts are very clear and are well established. There are uncertainty due to presence of chaos, the resolution that is not really a fine resolution. And the question may arise, will we be able in the future to model climate, predict climate in an effective way? Because again, what we are now predicting for 2050, it's not a real prediction. It's not like the forecast of the weather. They will tell you tomorrow you are likely to get 10 millimeters of rain. When we hear somebody saying in 2050, if we don't reduce the emissions, we will cross the plus 1.5, therefore not meeting the Paris Agreement, this is not really a prediction. They call them projections, estimates. So the question may be, will we be able in the future to predict the climate with certainty? This is a more philosophical than a scientific question. Science now says that it's not possible with no uncertainty. Science says that it will be possible to reduce uncertainty. If your question is, will we be able to bring uncertainty to zero? This is more philosophical than scientific. In my opinion, no, because chaos is chaos. And even if you improve the definition of the models, if you improve the measurements of your input variable, chaos is such that even a tiny mistake, a tiny error can give rise to completely different scenarios. So now the evaluation is statistical. It's not quantitative. Statistical means that we use several models, several different assumptions, and we get a lot of predictions, several measurements, because if a measurement may be affected by an error, what is the way to see the effect of the error? To take the measurement, different values for these measurements in order to account for the fact that temperature that I measure today may be 14, but maybe 14 plus 0.1 or 14 minus 0.1. So you run your model with different values for the data, for the input data, and you get an envelope of simulations. And this envelope of simulation, by the way, it is called ensemble simulation, gives to you the statistics. Okay, and let me talk a little bit more about scenarios, but I don't want to make it long. These are the different scenarios that now science is considering. Scenarios of what? Of future CO2 emissions. And it is nice to look at this link. I put this link here because the article is actually copyrighted, so I cannot put in my slides the figure that is therein depicted. Just let me open it. I think there is a nice picture here. Okay, this is the picture I wanted to get. 1 second. These are the scenarios. In the vertical axis, you see the global fossil fuels emissions. And in the horizontal axis, there is time. And you see the different scenarios. And in terms of emissions. So this is nicer to see than the slide that I am presenting to you. I wanted to put this picture in my slides and my website, but I asked permission and they asked me to pay like something like 150 euros. And then I said, what? Okay. So this is why now you see that I make reference to this slide. But you don't need really to know this. It's just fulfilling the purpose of giving to you an idea of the different predictions that we are making for the human impact on climate. I mean, I hope I succeeded in highlighting the importance of uncertainty. And I just want to give you some more details. So where does uncertainty come from? I said limited knowledge, chaotic behavior, etc. And I think that it is useful if I emphasize that first, methods for estimating uncertainty differ a lot between scientific disciplines. There are some scientific disciplines that are very efficient and they have the means for providing very good estimates of uncertainty. Like, for instance, prediction of weather forecasting, they can provide a very good estimate of uncertainty. Because basically, what is the difference between weather and climate? Weather works with a limited time horizon of the prediction, a limited lead time of the prediction. Weather is predicted for tomorrow. And about 1 hour ago, I said they are progressing and they are gaining 1 day of lead time of prediction every 10 years, which means that now in meteorology, what is now the reliability of a meteorological prediction? It's about 1 week. But if you go beyond that, and in climate you go to 2100, uncertainty increases. So there are some disciplines where uncertainty, scientific disciplines, where uncertainty can be defined quantitatively with good efficiency. Climate is still far from that. So climate modelers are concerned about 3 types of uncertainty. The forcing, solar radiation. We need to predict the solar radiation. Usually it is kept constant. So this is really a big uncertainty. And then there is model uncertainty, what we call model uncertainty, which means that the model doesn't provide a perfect reproduction of the reality. And then there are the initial conditions, because this is not easy to explain and to understand to explain to an audience with a very different background. These models, I make a long story short, very often describe not the variables, but the changes. In fact, I said that they are maybe more reliable in describing changes rather than the variables. Why they describe changes rather than the variable? Because the equations are differential equations. If you don't know what a differential equation is, just forget about this. It's not something that you need to learn for the exam, but from a conceptual point of view, just keep in mind that the conservation laws sometimes describe changes, not the value of the variable. So if you want to describe the value of the variable and you have an equation describing the change, you need an initial condition, an initial value. So if I say that tomorrow there will be 1 degree more than today, and the model is able to say this to me, I need an estimate of today's temperature to get an estimate of tomorrow's temperature. If I measure today's temperature is 10 degrees, perfect. 10 degrees is the initial condition. The model is predicting +1, tomorrow I will have 11. But without the initial condition, and the model is only predicting the change, I wouldn't be able to predict the temperature of tomorrow. The initial conditions are essential for climate models, but sometimes there is uncertainty because you cannot measure them for some of the variables. And sometimes chaos is such that if you make a tiny error in the initial condition, then prediction of 1 day, the error remains tiny. 2 days, a little bit higher. 100 years, huge error. And I don't think that really, you don't need to read this in detail. I just want to say one thing. I just said that it's not easy to predict solar activity. We know from the past that there were changes. This cannot be predicted. And let's talk about emissions. Emissions, we consider several different scenarios, but actually, had we to predict what is the scenario, this is really hard to predict. How can you predict what will be the result of these mitigation policies? And think about COVID-19. COVID-19 has shown us that when we talk about nature, when we talk about human society, it's difficult to predict what may happen and to predict how human communities may react. You may have heard that after Russia declared the war to Ukraine, Mario Draghi said that we need to reactivate our energy production resources that were using fossil fuels, okay, coal. And this means that we have to make a step back in our policy for reducing emissions. If we have to compensate the use of natural gases by burning fossil fuels, this is something that probably we couldn't predict, and something that is probably bringing us to a step back in our actions to mitigate climate change. So you understand this uncertainty is really something that we need to consider, which doesn't mean that the models are not useful. The models are very useful. We need them. We need to make predictions. But on the other hand, we have to be aware that what kind of predictions we are getting. Okay. Let me just check because I think I already said most of this. Yeah. And now let me show some graphs so we can come to the conclusions. And you see here a comparison between, which is a kind of verification of the output from a model. You have the global temperature here. The green line is given by observations, and the blue and the red lines are given by two different models. The Hadley model, so the model that is run by the Hadley Center in the UK, which is one of the most important climate models that we have available today. And another is what is called the Canadian model. It's run by the Canadian Climate Center's Canadian Climate Center. And it's from 1900 to 2000. And here you can get an idea of the discrepancy between observations and models. And also you can get an idea of the trend. Look, if you smooth these curves, I think that both models are successful in reproducing the change in temperature with a different progress along time. So it's not bad, but we are talking here of temperature at the global level. So it gives to you an idea. And let me just check how many slides I am missing. Okay, very good. Let me skip this because I already talked about this. And what is this slide saying? That a way to estimate uncertainty is to run different models and considering the envelope, the ensemble of the predictions. And then from the ensemble of the prediction, you may compute an average, or you may compute, if you know something of statistics, a probability distribution. And let's say that to simplify the last thing that I said, you may get an indication of the most likely future together with some variability, estimated variability of the prediction. Okay, and there is one thing to say. The criticism that some people address, if you evaluate uncertainty of future predictions by an ensemble of models, if all the models are wrong, because it's wrong the underlying assumption that all of them use, then you don't get a good estimate of uncertainty. You just get an envelope of wrong models, but maybe that none of them is correct. So even if you compute the average, maybe not a very useful information. And so it's important to notice that even when we are presented uncertainty of climate predictions, this uncertainty estimate is uncertain. And it looks like a game of words, as we say in Italian, but it's actually, it is just important that we are aware of the uncertainties that science still has, which is fine. I mean, it's perfectly fine that science has still uncertainties. And then when it comes to action, this becomes really important, because in order to devise actions, you need a prediction and an estimate of uncertainty. If you are not given an estimate of uncertainty, this is the word by engineers, you cannot make any reliable design for any action. So I mean, uncertainty is not negative, it's positive. I mean, once I am given an estimate of uncertainty, I can solve the problem. Engineers are used to deal with uncertainty. You are used to deal with uncertainty every day. You don't realize it, but every day you are used to deal with imprecise information. Like when you go to the bus stop and you see the timing, then you realize maybe 10 minutes late, and then what happens? The same thing for an engineer. I get a prediction of future climate, fine. Maybe 10% more. Okay, let's see what we can do to cope with this. I mean, uncertainty shouldn't be seen as a limitation. It's information. Okay, and here is an example. Global warming projection. This is an ensemble from the most important models that are running today. They are about, you see the number, they are about 13, 14 models, 15. And you see that in the reproduction of the past, the spread is lower. When you go towards the future, and this is fine, the spread increases because they are in a way tuned to reproduce the past. We are talking about global temperature, okay? And anomaly. What does it mean, anomaly? It means the change with respect to the long-term average that we know during the instrumental period. During our observations tell us what is the average temperature of the Earth. And these are the predictions for the future development. And you see that the most optimistic, this is business as usual scenario. So emissions that continue to increase. The most optimistic gives 2100 plus 2. We are now at, you see the level now, 2020 is about plus 1. The spread is more or less around plus 1. And then the spread increases and goes from plus 2 to plus 4.5. Okay, and there is one thing, this is my last slide today, give me 2 minutes. climate models are not the only models that, let me say again. GCM models are not the only climate models that we can use. There is a small fraction of people in the statistical community that are proposing to use statistical models to predict the future climate and to generate future climatic scenarios. This is something that is coming during these years. It's now coming, and you may think that statistics is not good because statistics is like tossing a coin. It's not like that. Statistics may profit from physical basis, from physical knowledge, and the statistics is a very efficient way to deal with uncertainty. Actually, these techniques are for now used to obtain very local information. Where climate models are known to be not precise, for instance, if you're interested in likely scenarios for the climate here in Bologna for the future, then I would say you should use a statistical model to generate it, because for the very local information, the climate model may be, and especially for variable other than temperature, may be not efficient. But you can use the climate model to condition in a way to support the prediction that is done by statistical model. So let me summarize in 1 minute what I did today. Today, I talked to you about information in order to inform climate action. And I said that information is mainly taken from data, and they can be observed, proxy, and given by climate models. I said all these three sources of information are affected by uncertainty. If I had to rank the less uncertain, but this is an opinion with that some climate modelers wouldn't agree with, I would say that observations are more trustworthy. I speak as an engineer. And then there is proxy, and then there is climate models. But as I said, uncertainty is not a problem as long as we can quantify it. And I think that all these three sources of information should be used together. So if you see somebody trusting only observed data and distrusting climate models, I don't think it's a good approach. If you see somebody doing the opposite, I don't think it is a good approach as well. Okay, I just closing asking you two things, or let me say one question. Do you have any question for me? And then I close by saying, remember that next Monday with the same timing, there will be Professor Veronica Rossi. I think it will be an extremely interesting lecture. I really encourage you to pay attention to what she says. She's very expert in climate of the past, and I will be attending remotely. Thank you very much. I close the registration and then I speak with the interpreters.